So hello, welcome to lecture 21. Today we'll be talking about problem solving. Before we do that, we're going to go ahead and do a quick check-in on homework 7 because I got the sense that some people found homework 7 kind of challenging. We're going to focus in on different types of problems we can solve using coding. We're going to talk about what questions, how you want to just try to approach those problems in general. And then we're going to look at questions that you want to ask and apply them to practice. So we're essentially, this entire lecture is all about coding problems that you might see in this class, but also problems you might see in LeetCode. So if you're interviewing at a company, whether it's a big company like Google or a small company like a startup or somewhere in the middle like NCR, I mean, NCR is actually pretty big, and Coxcom and all the other companies, chances are they'll ask you some questions around how to write some small piece of code, right? Some of you have seen LeetCode before. It's a website that just shows you all the different types of questions that there might be and tries to create like a database essentially of questions you can practice on. And we are trying to talk or give an introduction today of how you might approach solving these problems. Now, give me a yes in chat if you've tried to solve LeetCode problems before, or no if you've never tried to touch this problem, touch these before. Okay, we get a few yeses in chat. Actually, pretty good yes to no ratio right now. This stuff can be really hard, right? Like I imagine some of you tackling these problems might feel really intimidated or feel like these problems are in general just very hard to grasp. And the key to remember, and the key that we're going to focus in on today is this isn't one of those topics or ideas where you can just like learn everything there is to know and then suddenly you're magically good at this. This is the sort of thing where you have to practice day in and day out for months before you start seeing some progress. And oftentimes you will face challenges and frustrations along the way, right? I'm not saying this to deter you, but I just want to make sure that your expectations of what you're going to get from this lecture are clear. We're going to talk about the basics and overview of how to approach these problems, as well as go through some examples and talk about what kind of questions you might want to ask, and just go through some examples for you to start getting your head around all of this. But not necessarily, you're not going to be an expert by the end, right? I think most of you feel good about that, but I just want to make sure you all understand what I'm expecting you to get out of this lecture, right? So let's just go ahead and first answer the following. I'm asking you about homework 7 now. So I know that homework 7 was the last week's homework. It was due last week, and I just wanted to get a check in how you felt that homework went for you. Specifically, I want to know, was it challenging for you? What did you get stuck on, if anything? What would have made your experience better? Go ahead and type in chat if you have some thoughts. I'm not looking for anything in particular. I'm not looking for a right answer. I'm just getting a vibe right now overall of how y'all are feeling about homework 7 in particular. Was there anything that made your life easier, made your life harder? Is there anything you wish were different compared to how it actually went? Some people found it challenging, but in a good way. Some people felt like it went well. Some people felt like there was just a rough week in general, so didn't really have a chance to focus in on it. That's fair. Struggled with the last two in runtime. Not bad, hard, not the smoothest. Greedy isn't the worst. All right, so let's go ahead and do a poll here. I want to take all of this and maybe do a little bit of a more formal check. There's 5 questions in this poll, asking you whether or not it felt easier, the same, or harder, if it took shorter, about the same, or longer, and whether or not you found the homework party video helpful, whether or not there was one question that took the longest to answer, and when you were coding, what was the hardest part there, right? So I ideally would like all of you to participate just to get a good sense of how everyone in the room feels. Again, these are anonymous, by the way. Like can't tell who voted what. And I'm only doing this because I want to learn more about how you felt about that homework. We have one more homework for homework 8, which will involve coding, as I've said in the past. This will be the last coding-based homework. Everything else will be more nice to you. But I just wanted to get a sense of how you felt about the homework based on what you experienced. All right, there's still about 20 of you who haven't voted, 15 of you now, nice. We actually got different votes and different results from other sections. Please continue voting. Let's try to get this to 100% if we can. All right, there's still about 3 of you who haven't voted, so 2 of you. Can we get the last person to vote? All right, so let's go ahead and take a look. Most people found, okay, about half of you found that it was about the same as usual, but then the other half found that it was harder than usual, which is fair, right? This was on the more challenging side, so homework 8 will be a little bit on the more challenging side as well. That's just, I'm not too worried about it, but at the end of the semester, we're going to look at some more challenging topics, some more challenging homeworks. Don't let that scare you or make you feel too discouraged. Most people found that it took about the same, but a good deal of you also found that it took longer than usual. That's normal as well. Most people found the homework 7 party to be the video felt some sort of useful, which is good. I'm glad that it helped. And it looks like the question that took the longest to answer, it was between the coding and the last question where we asked more about Kruskal's and kind of trying to figure that out. And then for coding, the hardest part was coming up with the idea. Okay. Right. Okay. I'm glad that the lecture or the homework party video, which was basically a lecture, it was an hour and 40 minutes long, so it was essentially an extra lecture, helped you with the homework. I'm glad that it helped. Let's just very quickly go over homework 8. Remember, homework 8 is released and it's due next Friday, or this coming Friday, rather. I'm not going to post a video. It turns out that everything I wanted to talk about is already in lecture 20. Lecture 20 about dynamic programming. We go over pick trees and the way you want to write best value for fused, both the recursive version and the dynamic programming version will be very similar to pick trees. All right, so if you go back and watch that video, I promise you, you'll understand a little bit more of it the more times you watch it, or the second or third time you watch it around. And I give you some hints here on how you might approach the recursive calls, and I gave you some Piazza posts that your fellow classmates have written that I think are very effective and do a good job of explaining this in more detail about how pick trees works. Because if you understand how pick trees works from lecture, then I promise you best value for fused will come more readily. It will become a little bit more straightforward. Now, likewise, lecture 20 helps you with a dynamic programming version, which is what question 2 is asking. I give you some more hints here. And there's videos for the Bellman-Ford section, which I'm not too afraid of. If you just watch these videos, they're 9 minutes total. You should be able to feel good about the algorithm enough such that you can answer these questions. But if you don't, there's always Piazza. You can ask on Piazza if you get stuck on anything. There's also office hours. As you all know, because I keep saying, there's office hours right after this lecture. There's office hours on Wednesday from 4 to 5, 4:30 to 5 p.m. on in Eastern time. And then there's office hours in the evening here as well, right? If you can't make any of those office hours, you can book one-on-one appointments with either me or any of the TAs, and all the TAs know how to do the homework. I make them all do the homework beforehand, so they have a good idea of what to do. There are lots of opportunities, usually in the afternoons or the mornings, to book some time with them, right? So they're all available. And you can spend like 15 to 30 minutes with each of these folks, which I think is helpful, because if you are feeling intimidated by the program and you want some more guided help, they are here to help you. They are here to be kind to you and to walk you through it and to help you step by step, right? So if you feel like you're a little bit stuck on the programming aspects, remember, office hours is a thing. Is anyone not available at any of the times, either in the group office hours or in the staff office hours when you book an appointment? Give me a I can't make it in chat if you feel like none of those times work for you. So we have evening times using group office hours and morning and afternoon times using one-on-one office hours. Anyone feeling hard stuck in terms of the scheduling conflicts? Now it's the time to let me know. If you are stuck, you can always send me an email and we can work out some alternate time. And moreover, these office hours, no one comes to these, which means that if you actually want one-on-one help, just show up and chances are you'll be able to work in one-on-one with a TA or with me. And it's the same as booking an appointment, but it's a little bit easier because all you have to do is show up instead of use the UI to book an appointment here. All right. So I'm just letting you all know we're here to help. The point of this class is to help you learn. The point of the staffer to help you succeed. Okay, someone in chat called me out. Not everyone doesn't show up, but I'm saying right now it's really quiet. So if you felt like, oh, I don't want to go to office hours because it's really busy or everyone else will be there, it's a good opportunity. Everyone there wants to learn, so you're among peers who are have the same mindset as you. All right. Extra credit will be added toward the end of the semester. Yes, it will be toward the end of April. Chances are I will be focusing in on grading toward the end of the semester. Right now, we're doing as much as we can just to get grading in. I still need to wrap up exam 2, which in theory I should have done by today. I was supposed to submit the grades into iCollege this earlier today, but my cat had a medical emergency, like no cap, like had a minor medical emergency, and I was calling around vets to take care of him. He's good now. Everything's fine now. Nico's fine. But it was a little bit scary and touch and go for a little bit. So we wanted to make sure things are okay. Was there a question? It looks like someone raised their hand. All right. Well, Nico's fine now, so don't worry. But this is why, for example, some of the grades aren't fully entered yet. Life happens. Okay, if you have a question, feel free to unmute and ask. Otherwise, we're going to move on. Okay, someone raised their hand. Let me know if you still have a question. Okay, no question. Got it. Okay, so let's go ahead and dive into the topic for today. So we're talking about solving coding problems. So essentially problems that show up here, basically, right? If you don't know, as I said before, LeetCode is just a platform that stores all sorts of different kinds of coding challenges. And the expectation is, they'll give you a prompt, they'll give you a way to type in your solution, and you'll try your best to write your code to implement the code function that they're asking you to write. Right? There are other platforms like, for example, HackerRank that do something similar. HackerRank is oftentimes where I would start and then move on to LeetCode if you're trying to start from scratch. Coding questions are generally broken into 3 distinct flavors, and they're kind of ranked by level of difficulty. The first type is just explain or build something you've seen from class. Like, for example, implement a hash map, write breadth first search for a tree, or write breadth first search for a graph, whatever. It's just a direct application of what you've learned in class, which is, understanding, remembering, applying that layer of Bloom's taxonomy. It's relatively straightforward. You might see this in your interviews. Some people just want to see how well you've retained the information from class, because if you've learned the stuff from class and it sticks in your head, chances are you can use it. You would be able to learn stuff on the job and have it stick in your head as well, right? So that's the first type of question. And then the second type is to solve a computer science problem directly. What do I mean by that? Well, it's something like this, right? Something that we haven't learned directly in class. For example, if I give you a list of integers, return the kth smallest integer. That is one possible example, because I didn't never explain to you exactly how we would do that. How to print elements of a binary tree in a certain pattern. Maybe it is related to some traversals and some print methods you've seen in the past, but it's not exactly the right one, or it's not exactly like a depth first search or a breadth first search, something like that. So oftentimes for problems like this, we're testing your application and analysis skills, right? Someone asked, hey, didn't we actually do kth smallest? Yeah, we kind of secretly did. So I actually sneak in LeetCode problems for homework sometimes to either have you analyze it, but I've never asked you to write one, at least not without a lot of help or like a homework party or something like that, right? So here we want to, for example, the trick here, or the motivation and the steps you have to take is first, figure out what existing knowledge you need to use, and also figure out the twist. Oftentimes when you're trying to solve this problem, there's like a twist or a trap or a trick to it. And these types of problems are maybe a little bit more challenging compared to what you had before, right? But the idea here is you want to take the existing knowledge you have and maybe use it in a slightly new way, or add 2 ideas together to solve something in computer science that is, a direct sort of application of what you've learned. Lastly, we have the third layer, which is to solve a real world problem. So, for example, that might mean given a list of customer wait times, return the minimum total wait time. Given this 2D array that represents a maze, show if it's possible to leave the maze by only making right turns. These are all kind of like the word problems you saw in elementary school if you went through an American education system where they have like, oh, Sally has 4 apples and then George takes 2 of them. How many apples are there left, right? Or something like that, where it's very much, you have to take this problem and translate it, must translate into a CS problem, right? Word problems that effectively require you to translate up into this. And then from this level, you have to translate and figure out how to map it to something that you've actually seen in the past, right? So in general, these are like kind of the 3 layers of problems you might see. I didn't talk yet about how to solve these problems, so let's do that now. Before we move on, a real world problem, really what we're asking is your ability, we're testing your ability to synthesize, your ability to evaluate. You have to take the problem and see on a high level how to translate that into a computer science problem. And that requires a lot of maybe thought and experience and practice and a little bit of luck, right? Okay, so in general, how do we solve coding problems? One, you have to understand the problem. So that means coming up with some examples, making sure you understand the edge cases, how to handle maybe some base cases, stuff like that, right? So if I give you, for example, a problem on trees, your question might be, okay, is this example that I came up with, does this give you is this accurate? Like, will it produce this result as you've described it to me? Or maybe what happens if I give you the empty tree versus a tree with only the roots, or a tree that's skewed left or skewed right? You have to understand all of the aspects of the problem before you move on, right? We're not going to baby you or feed you spoonful by spoonful how to understand the problem. That's part of the challenge whenever you're solving coding problems. You have to understand what they're actually asking you to do, right? Then you have to come up with the idea, which is essentially the approach you need in order to solve the problem. Whenever we're solving homework problems and coding is involved, I always ask you, what is kind of the key idea? And in the homework solutions, always write, here's like the key idea or the approach you need in order to solve this problem, right? So if it's a tree, maybe the key idea is that we have to use breadth first search, but we have to use it in a certain way. Or maybe the key idea is like, first, let's sort the list and then we'll do something on top of that, right? And so the key idea is just like, what is the crux of the problem, so that once you understand that piece of knowledge, then the rest of the problem is just coding and implementing. That's not easy, coding, right? Building it out the actual solution, but at least then you can be able to solve it by hand. From there, you would actually need to code it out, which, obviously is a challenge sometimes because coding is hard. And it'll require you a lot of practice before you feel comfortable with this and be able to express ideas in code fluently over time. And then lastly, you have to debug your code and actually test it out, make sure it actually works, right? Unfortunately, there's not a detailed step-by-step approach apart from this. Like, this is like the general approach, but there's not like more details that I can add here to come up with an algorithm for any given problem, right? It's as if I'm asking you, like, I'm not going to be able to tell you step by step how to act like me, right? It took me years to get good at solving all of these problems, to be able to tell you exactly what the big idea is offhand, stuff like that. And so instead, for this lecture, we're not going to make you experts by the end of it, but we're going to teach you the series of questions that you might ask in order to be able to start the questions, start the approach, come up with the idea. And you're going to have to lean on past experience and generally do trial and error in order to be able to do this effectively over time, right? So how do we come up with the idea, right? I try to emphasize it the way I wrote it with capital T, capital I. Essentially, we're going to spend a lot of time just looking at different problems and thinking about how to solve each problem using algorithms, right? We're not going to focus on coding. We're not actually going to write the code for each of the problems. We're just kind of come up with the idea and then stop there and move on to the next question. Half the time interviews are hard, and like coding questions in computer science, like on homework and stuff like that. Like if I pick any of these homeworks where you actually had to code, they're a challenge because you have to like kind of magically get the idea from thin air, right? It feels like sometimes you just have to pull something out of the top of your head and somehow it magically works out, right? The only way to get good at this is to practice. So we're going to put in some time today and walk through a bunch of examples. So again, the motivation is for you to understand each example, think about how you would come up with the idea on your own, and then watch as how I explain how I come up with the idea, some questions you might want to ask and stuff like that, right? If you have any questions or concerns, now's the time to ask. As always, feel free to interrupt me at any point in the lecture. But if you want to clear up any misunderstandings or ask some questions or clarifications before we dive into this, now's the time to ask. Okay, so let's move and look at the type of questions you might want to ask. Whenever we have problems like this, there are a laundry list of things you could ask. So first thing I would ask, which is the most important, at the top here is, do I understand this question and can I come up with an example for myself? And this is a question that we're always going to ask. We're always going to ask you to do so that you can practice this and really understand what's going on. Next, you want to make sure you check your assumptions. Are there any edge cases to keep in mind? Someone asked in the previous section, what did you mean by edge cases? Edge cases is just a fancy way of saying like, okay, if you have to solve a general part of this problem, like if you have to solve this problem in general, are there any specific examples where things will like be confusing or your code has to be very careful handling those? Like for example, if I were to ask you to find the 8th biggest element in a list of integers, one question that might pop into your head is, what if the array is only 7 big? If the array is only 7 big, what do you want me to output from my function, right? So that's what I mean by edge cases. What are some cases in which, given the context of the problem, I might not know the answer to or that I might have to pay special attention to, right? From there, once you have all of that background context, you want to focus in on like, okay, are there any algorithms that I know of that I can use directly? Are there any data structures that I know of that might make the problem easier to solve? Is there a way to take this problem and transform it into an existing problem I know how to solve? Is there a way to modify an existing problem, an existing algorithm to be able to solve this problem? What information about this problem should I focus in on? Maybe there's some part of the problem that's specific or important that I need to like use in order to solve the problem in general. And lastly, are there any dumb tricks that I have to know about, right? Computer science, to be frank, is filled with tricks that make you feel dumb. Right? Once you learn the trick to solving a certain problem, you smack your hand on your head and you're like, damn, if I only knew that, then I would have been able to solve this, right? You can kind of see the way to approach it once you memorize that dumb trick. Go ahead and type in yes if you've seen or heard or understand what a sliding window algorithm is. No otherwise. Sliding window. So I'm asking you, sliding window, has anyone explained this to you? Well, sliding window, for example, is a dumb trick. 2-pointer is a dumb trick. If you just search sliding window algorithm in Google, what you'll see is there's an entire section in Geeks for Geese where they show you some examples of what sliding window actually means. It's usually something you'll use on array functions, you'll use on string functions, you'll use on list functions, and it's not hard to understand, but if you've never used it before, then you'll get stuck on those types of problems. It allows you to oftentimes traverse and find the solution to a problem in linear time. Likewise, if you have 2 pointers, it's a related but slightly different approach to solving certain problems that you want to know about. Okay, there are many more dumb tricks. We'll see a few dumb tricks in this lecture today, but there's no way to show you every single dumb trick and have you memorize it and then be good. You kind of have to stumble upon them every problem you solve and make mistakes on, and then once you see the solution to those problems you get stuck on, you realize there's a dumb trick to it and then you memorize it, right? Let me make it clear, you shouldn't feel dumb if there was a problem that involved a dumb trick. What you should do is proactively try to memorize it so next time it's no longer an issue, right? I call it a dumb trick because I think I call it dumb because it doesn't make, like, it makes you feel dumb, right? You're not clever for knowing it. It's just something you need to memorize. And then I call it a trick because, again, once you know it, it's no longer an issue, right? And once you understand how the trick is done, like a magic trick, it's no longer magical or frustrating or baffling. So what I mean here is that there's a collection of things that over time, once you learn about them, they become less scary, which are different than what we learn in here. right? Like obviously you need to learn the general concepts of trees, but there are some dumb tricks within trees where once you learn those dumb tricks, writing tree algorithms becomes a little bit easier, all right? So let's go ahead and dive into our first problem. Here, we're going to go ahead and try to take in an unsorted array of integers and return the kth smallest number from it. Now, this is hopefully something that's relatively straightforward. So I'll give you all 10 seconds to answer the following, right? What kind of problem is this? Well, I said there were 3 types at the beginning. So let's go ahead and answer. A, is it a, don't type it in yet, but is it a direct application of what we've learned? Is it B, a CS problem? Or C, is it a real world problem? Right? A, B, or C. Go ahead and type in chat. What do we think? Okay. We're getting actually a lot of different answers. Some A's, some B's, some C's. So I'm actually going to go ahead and classify this as B, a CS problem, because you can't take in, like, we never in class, like directly, okay, I kind of sneak this in, but we didn't learn in lecture, oh, here's how you solve the kth smallest problem, right? It's not exactly something that I need you to know in order for you to graduate algorithms or to get a degree in CS, right? You can get a degree in CS, be a very excellent computer science major and be an excellent programmer and have never solved this problem before, right? You can't be a CS major if you've never written breadth first search or learned about breadth first search on your own, right? So that's the difference between B and A. B is just the application of what you learn in class. So in other words, is this a class problem, right? A problem from algorithms? Is this a CS problem in general, or is this a real world problem? All right, from here, let's make sure we understand the premise. So if I give you, for example, kth smallest here, and I pass in a list, let's say, 9, 4, 3, 7, 6, 2, 1, right? And then let's say we want the third smallest element here, index from 0. Then we would get 0, 1, 2, 3. So we would get 4 out here, right? If I were to do this again and try this one more time, let's say I wanted to get the, the 6th largest element in here, index from 0. Go ahead and type in chat, which number do I output here? Right, everyone should be punching in 9, right? We're just trying out some small examples to make sure we understand this problem. Okay, so then what questions might you have before solving this problem, right? Before we come up with an idea, are there any edge cases? What edge cases do we want to worry about? I'll give you 15, 20, 30 seconds to think about this because it's kind of a complicated question, right? So we answered what kind of problem is this? We just went through and tried to solve this. Again, edge cases are this idea, and we come up with examples ourselves. Edge cases are just this idea of like, what are some cases that might be confusing here? What sort of inputs might be confusing that we don't maybe immediately know what we want to do here? Or what some sort of cases might actually cause some problems when it comes to implementing and writing a solution for this? Right. So go ahead and type in if you have any thoughts. So a lot of people are typing in, okay, what happens if we do this, right? If we do kth smallest and we have, let's say, an empty list and let's say a number here, right? We don't know what should happen here. Should we return null? Should we error? Should we just crash, right? So we're going to assume what, this is a question we would come up with, and then the interviewer or I would clarify, hey, you can assume that k is in the range 0 to n-1 inclusive, right? So then you can say, okay, well, you could get the 0. Someone asked also, like, what happens, what is, this, right? Is this a valid output? And yes, the answer is yes. Someone else might have asked, hey, can you handle negative numbers? You can have negative numbers in the array, but you can't have negative numbers in K, right? So then the question the questions I want you to come up with is just, how do you think about this, right? So another question someone asked is, how do you handle duplicates? So a question is, what happens, for example, if we do this, if we have kth smallest of, let's say, 4, 4, 4, 4, right? And then 3, 2 here, then we would want, in this case, just 4, right? Or if we want, let's say we had 1 and then 2, we would still get a 4 out because the 0th smallest is 1, the second smallest, the first smallest is 2, and then the second smallest would be 4, right? Can we modify the original array? Let's say yes, right? So these are all the types of questions I would expect you to ask. And these are questions you're totally allowed to ask in the context of an interview, and you should, because it shows that you're thinking and it shows that you want to, make sure you understand the problem well enough so that your answer is going to be robust, right? This is what I mean by edge cases. I just mean, like, how do we handle all of these cases where the things are a little bit weird, or things might not necessarily be obvious, right? Which 4 do we care about? It doesn't matter. Let's just assume all 4s are the same here. So we don't care if we return the first 4 or the third 4 or whatever. All right. So at this point, we've answered a bunch of different questions. There might be other questions we want to ask, but I think the most relevant question at this point, since I think most of you already know what we're about to do, is what is the idea, right? In other words, how would we approach solving this problem? Now, some of you see this problem so easy, think this problem is so easy that you don't really have to think about this as a type B problem, right? It's just like such a direct application of what you've learned in class. So I'll give you all 10 seconds to think for yourself. How would you approach solving this problem? If you had to write like in words how you would approach, given an array of integers, giving me the kth smallest integer. Go ahead and type in chat now if you have it. What do y'all think? Right, so we just sort the input array, then return array of k, and then you're done, right? Nothing scary here. If we have an input here, for example, this input, and we just sort that array. So for example, if we have this as the numbers that we care about, and we want the third smallest element from index from 0, then first we want to sort it. So we would get 1, 2, 3, 4, 6, 7, 9. And then the third smallest from here, index from 0, 0, 1, 2, 3, would give me 4, right? So that's how we would come up with the 4 here, right? Not super scary. We start out easy-ish, right? Straightforward, at least. And this is almost a direct application of what we saw from the sorting, right? From the sorting sections. Now, okay, if we get this, the next question I would ask, right? And, sometimes you would ask different questions. Sometimes you ask the same questions. But in this case, what is the runtime of this approach, right? Let's go ahead and take a minute and see if we can understand it. Let me go ahead and stop sharing my poll and share a new poll. Let's just go ahead and do runtime. Let's assume we can't use radix sort. Let's assume that the built-in sort that you're using is Java sort, and Java sort, in the best case, is going to be log of, well, not going to be radix, all right? So for example, it might use quicksort, it might use merge sort. You'll have to read through the documentation here to really have a 100% clear idea. But let's just assume we can't use radix sort, and that radix sort is banned. Now you can always mention in the middle of an interview, hey, we could use radix sort here since this is an array of numbers, and that's like bonus points. But for the most part, the canonical answer is going to be based off of a comparison-based sort. So really, what I'm asking you is, if you have to use merge sort or heap sort or something like that, what would be the overall runtime of this algorithm? How do I define in? In here will be defined as the number of elements in the array. So we said it's an unsorted array of in integers. In is this in here. All right, there's still about maybe 15 of you who haven't voted. Go ahead and vote now if you haven't already. Are we asking about the worst case? Yeah, we're pretty much asking about the worst case. I mean, it won't matter either way. Worst case, best case is going to be the same. Yeah, sorry about the siren. I'm living right next to a street, even though I'm like 5 stories up. You can hear fire trucks sometimes because we're next to a fire station. All right, let's go ahead and end the poll. A lot of you said that this runtime should be O of n. some of you said that the runtime should be log of n times n. How long does it take to sort an array of size n if you use merge sort? What's the runtime of merge sort? The runtime of merge sort, which I always have to reiterate, is going to be O of n times log n, right? If you don't remember, that's fine. Just memorize it. Merge sort, sorting in general, any comparison-based sort is going to take n times log of n. All right, we know that this is going to be the bulk of the thing that we have to do when we're solving the problem. We know that this thing, returning array of k, is going to be O of 1 because anytime you look up an element in an array given an index, it's going to take one step to retrieve it. So the overall runtime, assuming we can't use radix sort, should be something like O of n times log n, because we had to sort the entire array of n elements, right? We don't know how many elements we need to grab from here. We could want the very last element. We could want the very first element, but we don't know. So given that, we have to sort all of it. And if there are n elements that we want to sort, then the runtime for sorting them, assuming we use something like merge sort, is n log n. You can actually look at the documentation for Java. You can just type in sorting Java and then click on the Oracle documentation. Oracle is a company that helps build Java. And you can look in the different kinds of sort. There are different kinds of algorithms that they actually use. Sorting numbers is different actually from sorting objects. They'll use a merge sort for objects, and they'll use tim sort. But they won't here. They'll use like a quick sort or something for numbers, because quick sort is fundamentally just going to be faster in real life, even though merge sort has the better overall runtime. All right. So this is what we would want for number 1. Give me a smiley in chat if you're feeling like you're with me right now. You're feeling good about this lecture. Oracle just got slapped down in the Supreme Court. Yeah, that did happen. Oracle versus Google, where Oracle tried to sue Google for coming up with an API that looks similar to Oracle's when they came up with the Android SDK, which was kind of silly. We let big companies do big company things. Let's go ahead and take a look at the next one. We're going to take some time to try to understand this problem. Essentially, this is very similar to the problem we just looked at, but now we have to tackle this a little bit more differently. We want to do better than n log n. N log n was the algorithm we just looked at. We saw that if we sorted all of the array, right? Approach number 1 was to sort the array. Sort the array, then return the kth element in the sorted array. Now we want to come up with something that does better than n log n in the worst case. I'll give you all about, let's say, 30 seconds to think about what have we learned in class that might be useful here, right? Let's go ahead, just take a look at the topics in the course website, go to the website, take a look. Is there anything here that sticks out to you? Anything that you feel like might help you here? We're really just like trying it out. Remember, radix sorting is still banned. If we'd had radix sort, then obviously we could do this in better than n log n time, because we would just sort the array in O of n time, because radix sort is linear time sorting, and then we could just return the kth smallest element. But let's just assume for a second that radix sort is banned. All right, I'll give you another 20 seconds to think for yourself. Type up your answer, but don't hit enter yet, and then we'll look at it together. Oops. All right, go ahead and type in chat, question mark if you're not sure. Otherwise, give me your best guess. And it's okay. You're expected to see a lot of question marks this lecture. You're expected to type in like question marks a bunch, right? Honestly, a lot of these questions, I'm showing them to you so that you see them for the first time ever. And if you're seeing them for the first time ever, you're not going to be able to come up with like a brilliant solution. All right. A lot of people right now are typing in question marks, but people also are maybe suggesting, hey, what if we use the heap? All right, so let's try this. Let's try this. Hey, what if we use the heap? That's the question we have here. All right, so the idea here is that we'll have a min heap. The approach number 2, add all the elements from the array into a min heap. Then, if you have a min heap of n elements, what would you want to do in order to get the kth smallest element from it? I'll give you all 10 seconds to think about it, and then we'll all hit enter. Right? What's the next step from here? I think someone already typed it in chat, so if you're not sure, you can scroll up and check it out. All right, go ahead and hit enter. What are we doing here in order to get the kth smallest? You just call extract min, right? Call extract min k plus 1 times, right? Because you need to count for the fact that you extract the 0th element first, the 0th smallest, and then the first smallest, and then the second smallest is indexed from 0. So you actually have to call it k plus 1 times, right? That's really important that you get the right ordering, right? Off by 0 here matters a lot. So let's go ahead and see how this would work. We would go ahead and let's make a new array. Let's say kth smallest here, and we would have 4, 3, 9, 8, 1, 2, 7. Let's add some more numbers like 5 and 6. And so we would output, in this case, we would output, let's say, the third smallest here. Right, so then we would need to build a heap. Let's just imagine we built a heap. And since this is a min heap, we know that our heap would look maybe something like this. I don't know exactly what the heap would look like, but let's just pretend like we built a heap. So after calling add, how many times do we have to call add? If we had to add all the elements into the array, into a heap, how many times did we actually call heap add? Type it in chat if you have it. Right, there's n elements. We throw them all into the heap, so we call it n times. So after calling add n times, right? Heap add n times. Then we're gonna go ahead and have an array that maybe looks like this: 1, maybe 3, 2, 5, 4, 5, 6, 7, 6, and 9, 8. Right? Like it really doesn't matter. It's not gonna be fully sorted. Remember, a heap is only representing, it only maintains the heap property, which means that if you drew this out, we would have 1 as the root of our heap, right? Because it's going to be a tree. It'll have 3, it'll have 2, right? It'll have 4 here, and 5. And as long as every element is going to be bigger than its parent, then the heap property is being maintained here, right? Which is why I'm allowed to do something like this. I don't know if this is actually what the heap would look like after we add all of the elements, but this is one valid heap that has all of those numbers we care about, right? So we have all of these numbers. Every single level, every single node has a value that's larger than its parent's value because we're in a min heap, all right? So then we're just going to call extract max k plus 1 times. If the value here is 3, then we're going to first get out the 1, right? And then there's going to be a lot of shuffling, and then we'll get out the next smallest, which will be the 2, right? And then we'll do it again. So we'll get out the 3 next. We'll get out the 4. And that will be the final element that we'll output here. And that's how we get the answer, right? We know that this should output 4 if we're trying to get the third smallest thing indexed from 0. Oops, that should be a 4. So if we call extract max a couple of times, extract min exactly n plus 1 times. So k plus 1 times. So 3 plus 1 gives me 4. I call extract min once, got me the 1. Call extract min the second time, got me the 2. Call extract min the third time, got me the 3. And then lastly, I return the last extract min, which was 4. Right? Now, some of you are already asking this in chat. What's actually the runtime of heap add and extract min? If you don't remember, each time you call heap add and each time you call extract min, it's going to be a log of n, where n is the size of the heap. Now, if I have a heap of size n, and I call heap add n times, because we said so before, that's going to give me O of n times log of n for all the times we add, right? All the times we did heap add. Now, just to clarify and continue on this badness train, how many times did we call heap, extract min? We called it k plus 1 times. So k plus 1 times multiplied by the log of n times each time you call heap extract min will give me O of k times log of n, which means total we're gonna get overall. How do I spell overall? With 1v. We get O of n plus k multiplied by log of n, right? Now this is going to simplify to log n still, because if you think about it, k can only be from 0 to n minus 1 inclusive, which means that it's always going to be at most another factor of n, which means that it would be 2n, which means that it's O of n log n. All right. So approach 2 doesn't actually solve the problem, and that doesn't actually do better, because if we have a heap of size n here, then the operations are all going to take log of n, which means that overall our runtime is still kind of terrible. Or not kind of terrible, but like not as fast as we want to be, right? So type in same for the same runtime. We got the same runtime from approach 1 to approach 2 if you feel like you understand everything up until now. Question mark if you're a little bit confused, or if you need me to repeat anything. This was approach number 2. Right? So this kind of didn't work. But there is a trick, a dirty trick that we'll look at for approach number 3. Right? So let's go ahead and take a look. We're going to actually, let's go ahead and take a 5-minute break. We'll come back afterwards. No, do I want to do a break first or afterwards? Let me think about this. Yeah, let's take the break now. Let's take the break, and I'll give you a hint. You'll take 5 minutes. You can think about this on your own. Right? Yes, it is a low-key a cliffhanger, and I'm doing this on purpose so that you all have some time to think about it on your own. So hint for approach number 3, which we're going to look at right after this, use a max heap. Make the max heap smaller than the min heap you were using. Right? It's kind of a dumb hint, but it's also kind of a dumb trick. I'll give you this as a hint. We'll take 5 minutes. We'll come back at 6:22, and then we'll solve this together. When will exam 2 grades be graded? They are frankly already graded. I just haven't had a chance to finalize the grades and put them in. There are some tweaks I want to make to how we graded certain questions. There's some typos and mistakes that I am looking at and fixing in terms of like I review every single entry to try to make sure that at least we just didn't forget to grade anything and stuff like that. And that takes a lot of my time, right? I'm the final person who enters the grades to make sure that you don't just get something that's wildly off. And we'll still have probably some small typos or mistakes that we will address afterwards, but that process takes time. I'm trying to get it done tonight. I'm trying my hardest, right? So you should, here's hoping, knock on wood, be able to see the actual grade you'll get for your section by the end of tonight. I'm not going to go to sleep until they're finally in. I'm going to put them into iCollege, and then I'm going to collapse and take a long nap. Right? That's my goal. I know that some of you have been waiting for a long time and are starting to feel a little bit anxious or frustrated. I apologize. A lot of random things outside of work, outside of teaching, keep coming up. Like, for example, making sure my cat stays alive. That was concerning this morning, right? No, you can keep my score. Yeah, the averages were definitely better than exam 1, right? Exam 1 was too hard. I already said so. But the averages look, on the whole, we're seeing a lot of Bs, B pluses, B minuses, some As, and some things less than B, which, you know, it happens. Again, we're taking a break, 3 minutes. We're just chilling. Go ahead, stretch, get some water, make sure you're breathing. You are now breathing manually. It's good to breathe manually sometimes. What if we made a list of size k, did a single for loop to update the values, and then return the last element? Well, you can't really know which elements you want to add to that array unless you're really careful, right? So try to think about the hint here about what we could do for a max heap. Yeah. I mean, I think I'm reading off chat. People are like talking about the exam and stuff, but I think that in general, I expect this section and the class overall to average around a B at the end of the semester. That doesn't mean everyone's going to get a B, but I'm trying really hard to make sure that the average score is going to be around there. So if you were a little bit worried about your grade, or if you're feeling like you're not sure where you're landing, if you've been keeping up with all the homeworks, doing the homework corrections, if you've been taking the opportunity to get points back on the quizzes, and you've been trying your best to do some of the more easy extra credit questions, so turning in things early, for example, then you will definitely be doing well in the class, or at least pass, right? So if you're getting wrecked on the exams, you still have a very good shot of passing. But if you're doing pretty good, or at least average on the exams, then chances are you're going to end up with some sort of B. And then you have to do above average, of course, to do to get an A. What would average be? Scoring something like 25 out of 40 would get you probably like consistently getting at least a C on the exams will get you a B in the class. Consistently getting a B on the exams will get you some sort of A in the class. Getting half the points, so getting a 50% on the exam, should get you a C in the class, assuming you're doing everything else in the class, right? So assuming you're turning in all the homeworks, all the corrections, all the quizzes, getting points back on the quizzes. That's kind of the design of the course, right? It's a lot easier to get a C than it is to get a B, and it's a little bit trickier to get an A compared to a B, and that's all by design. Homework 4 corrections were due yesterday. Yes. All right. Let's go ahead and take a look at this number 3 approach. Give me a blue in chat if you're ready to start again. Cool. All right. So we know that we want to go ahead and approach solving this a little bit differently. We know that the problem here, if we use a heap, is that if we use a heap that's as big as the array that gets passed in, then we're going to end up in the similar state as originally. So the trick I'm asking you to do is essentially, let's make another heap, but this time it's a max heap. And the max heap is going to hold, in this case, how many elements? Give me your best guess into how many elements this heap is going to hold, right? Approach number 3. Make a heap of a size what? What do you think? Max heap of size k, right? I don't know if this was just like the obvious guess, but k is basically, yeah, what we're going to use here. Add elements into the heap when the heap is full, right? When it reaches k elements big, remove one element, right? So extract max, and then add the next element from the array, right? So you're going to keep adding elements into the array. When it gets full, you're going to remove the biggest element and then add the next element in. And then at the end of the day, you're going to return heap.extract max one more time. All right. So let's go ahead and take a look at what this actually means in practice by maybe trying to solve this problem here. All right. So we're given this algorithm, or given this example that we have, we're going to try to see if our approach works on a small example here. Let's start by saying this. I'm not going to represent the heap as a tree all the time. I'm going to represent it only sometimes. At the very beginning, we know that our heap is going to be empty. And how many elements are going to be in this heap right now? Go ahead and type in chat. What do you think? How many? Sorry, what's the size of the heap that we're going to have? Actually, I think the heap should be k plus 1. So all of you, including me, who said k at the beginning, I think we all kind of failed there. Let me think carefully. Yes, it should be k plus 1, right? For reasons that will make sense in a second. So we're going to go ahead, and at the beginning, it's going to be empty. So there's 5 elements in here, right? If k is equal to 3, we're going to have 4 elements, not 5. If k is equal to 3, we're going to have 4 elements in my heap, right? The first thing we're going to add is what? Go ahead and type in chat. What's the first element we add into our heap? Hopefully this isn't too scary. I'm just asking you if we were to solve this manually by using the approach in blue here, we add 4 to our heap, and that's all good, right? Cool. So if we add 4 to our heap, then we're going to go and keep going and add as many elements into the heap as we can. So we're going to go ahead and add the 3 next, right? The next element in the array. We know that this is a max heap, so we know that the 3 is probably going to show up after the 4. We know that we're going to add a 9 next. So at this point, the heap will look something like this, right? We'll have a 4, and then the left child will be a 3. When we add the 9, we know we have to swap 4 and 9 since 9 is bigger than 4, so that should be on the top here. So we're going to go ahead. Oops. We're going to go ahead and swap those elements, right? So we're going to put a 4 where the 9 used to be and the 9 where the 4 used to be. Okay. So we know that this will look now it's like something like 9, 3, 4 here. All right. If you feel like you're with me right now, what's the next element we add? Go ahead and type in chat if you're following along. We're just adding the 8, right? So we're going to go ahead and add 8 to our heap. I'm just going to do this in my head, how we're going to add all the elements. I know in this case, since we're going to add 8, it's going to be the left of the 3. And then we're going to bubble it up. So we're going to actually put the 8 right here. And then 3 goes onto the where the 8 was inserted originally. And at this point, our array is full, right? Our heap that is represented by an array is full. It has all of the elements, all of the spots are taken. So now we have to extract max before we can add the 1. So we're going to add 1 next, but in order to fit it into my heap of size 4, I have to first remove the biggest element. So I'm going to go ahead and say heap that extracts max, which removes the 9. So 9 is removed here. 9 is removed to make space for 1. And what will happen is we'll move the 3 up and then we'll do some bubbling. We'll end up with something like this. We'll have 8, 4, 3, and then an empty space because we remove the 9, right? And then if I am keeping track of this in my head correctly, we'll add 1 and 1 will just stay where it is because it's a small number, right? And then if we keep going, we'll go ahead and remove 8, right? And we're going to make space for this 2, adding it into the queue, into the heap, but we can only do that after we make enough space to add a new element in. So in this case, we have to remove the 8. In this case, 8 will be removed. We'll move 1 into its place and we'll do some swapping. And then we'll have something that looks like this. Again, I'm doing the heap manipulation in my head. You'll just have to trust me. But we know that the leftmost element is always going to be the biggest because that's the top of the heap. And then some elements underneath it better be smaller than that. What do we do now? I'll give you 10 seconds to think about it. What are the next steps? And what do I have to do here? I know I have to insert the 2, right? So 2 gets inserted, so that's cool. What's the step after that? Actually, 2 gets inserted and it swaps with the 1 because 2 is a child of 1. Yeah. But what happens after that? Go ahead and type in chat. What do I do now? What do I put as comment here? Remove. Okay, we're getting a lot of question marks. Remember, every time we're trying to add things to my heap, all I'm doing is I'm going from left to right here in the original array. Oops. I'm going left to right in the original array such that we're going to add all the elements into a heap. And then when the heap is full, every time we have to remove the biggest element from the heap in order to make space for the next element that we're adding, right? So we're removing, in this case, 4, because we already removed 8 before. Now we're removing 4 to make space for this 7 that gets added in. All right, give me a 7 in chat if you're feeling better than the question mark that a lot of you typed in before. All right, we have to remove 4. 4 is removed to make space for 7, right? That's just fundamentally how we're expecting to do this. So heap now is going to have the 4 removed. So we know that it's going to have, in this case, a 3, 2, 1, and an empty. And then once we add the 7 in, it starts here, but then it very quickly swaps up. So it swaps against the 2. The 2 and the 7 get swapped, and then it swaps again with the 3. All right, this is what the heap will look like after we added the 7. We have to add the 7 because literally all we're doing is just following these instructions here, right? It might not be obvious why we're doing that, but what we're doing is just faithfully following the instructions that we have, and this is the heap that we have right now. All right. If you are feeling good about that, if you feel good about following the instructions, then what's the next step that we do here? After this step, what will we do, and what will we add? Go ahead and type in chat if you're with me. What do we think? Right? If you're still confused, go ahead and type question mark. That's totally fine. But ideally, hopefully, you can follow the pattern now. And again, we don't know why we're doing this, but we're just going to go ahead and remove. 7 is removed to make space for 5. Right? So in this case, our heap, if we keep going, we remove, in this case, the 7, and the new heap will look something like this. And then when we add the 5 in, we're going to go ahead and swap that up against the 2. So the 2 will be where the 5 used to be. And then the 3 will be where the 5 used to be, right? I'm not writing out the heap. It takes too long. But I believe the array should look something like this. And then one last time, right? Did I get this wrong? Oh, that's why people were confused. Why did we lose the 4 here? Wait, 0, 1, 2, 3. Dang it. I swore I did this before lecture, and I made the same mistake again. Last lecture, we had a typo here. But I think what we made a mistake for is that the size of the heap here isn't big enough. It should be larger than this. We shouldn't have removed the 4, and so we need to write down the fact that we actually need to keep a slightly larger array. Dang. Yeah, because we want to output 4 here, and we lost the 4 early on. So what we made a mistake on, or what I made a mistake on, is the size of the array should be, yeah, okay, it's because we're indexing from 0. So let's go ahead and imagine for a second that we had all of this. We had one more element here, right? I promise you this algorithm will still make sense, but I made a small typo here. I'm going to walk through it and explain what's going on after I fix the typo, right? What I'm saying is that because we index from 0, what we want to do is make as many elements. The size should be heap k plus 2 because k is the size index from 0. So the total number of elements that we're trying to keep track of should be 1 more than the total number of elements that actually exist in the first k, right? So when I say in the first k, if we index from 0, then that's actually k plus 1 elements. And so we're going to add 1 more to make this bigger. I think this should work. Really, it's just how we define everything, right? So we go ahead and we are able to add 9, fine. Then we add 8, fine. And then when we add 1, we don't actually have to remove the 9. So I have to go and update everything from here. All right. I apologize for the typo. I made this similar mistake in the previous section, and I feel embarrassed, but I swore I practiced this a couple of times, and I still keep making the same typo. But let's take a look. We add, at this point, we want to remove 9 to add 2. All right. So the reason why everyone was confused is because everyone's like, why are we removing 4? That doesn't make any sense, right? And you're right. It doesn't make any sense. We definitely I made a mistake there, right? Mistakes happen. We'll do our best to work over it. So in this case, we're going to go ahead and add a 2 after we remove the 9. So when we remove the 9, we move the 1 up. We swapped it with we move the 1 up to have an empty space, and then we have to bubble down. So we swap 8 and 1, and then we bubble down 1 more time to put the 3 here and then the 1 here, right? And then we're going to go ahead and add in the 2, like we said we would. So this operation leads to this heap. We can have a heap of size k at the current item if it's greater than the current max heap group item. Yeah, we could do that skipping. We would need to keep track of those elements accordingly, though. It's a little bit tricky, but that's an optimization that I'm not going to make in lecture, but that is definitely something you can do. And it is valuable to do that in a sec. But for now, let's just keep going. We're going to go ahead and say that, okay, at this point, we have to remove 8 to add 7, which if I do this correctly, looks like this. I'll go ahead and add, this is what I get for indexing from 0, by the way. It's all, indexing is all a terrible idea. We'll remove the 8. We'll put the 2 here for a second. And then we're going to go ahead and swap 2 with the next largest element, which in this case is a 4, right? Swap it with one of the children that is the biggest between 4, 3, and 2. And then we'll go ahead and add the 7 here. Once we add the 7, we actually have to swap up. In this case, swapping up means that we'll swap the 7 with the 3. Yes. And then we'll swap again the 4 and the 3, the 4 and the 7 here. Do I index from 1 often in practice? It really depends. Usually you index from 0. I'm just a little bit frustrated right now. I'm feeling frustrated because I got betrayed by indexing from 0, so I'm being salty at it. You actually generally index from 0 a lot. Ironically, sometimes you index from 1 when you're doing heaps, but it really depends. Okay, so we'll remove 7 to add 5. So we'll do this one more time. So we'll remove the 7. We'll move 3 up so that we'll have something like this. And I'll just go ahead and do the swap. We know that 3 and 4 will swap. And then when we add the 5 back in, we'll swap 5 with its parent, which in this case is 3. So this gets swapped up. And then we'll swap 5 with 4. Yes. And then we'll remove 5 to add 6. Please tell me this didn't break again. I think this works the way we would expect, but maybe I'm wrong. All right, so if we remove 6, or if we remove 5 and we add 6, what happens is we'll end up with, remove 7 to add 5. Okay, so maybe the skipping thing that people in chat were advertising, like maybe that's actually really important. So when we're trying to add the next element, yeah, okay, yeah, you're right. So someone in chat said that when you're adding a number, if that number is bigger than your current number, don't bother to add it in. And that's actually really important here. So if we wanted to remove 9 to add 2, that makes sense because 2 is bigger than 9. If we're trying to add remove 8 to add 7, that makes sense because 7 is bigger. Sorry, 7 is smaller than 8. If we're trying to add 5, we have to remove 7 to do it, that's fine as well. But when we try to add 6 and we're trying to remove 5 to do it, we don't want to do that, right? So don't remove 5 to add 6 here. And the way we found this out is by just trying out an example. Like we didn't know what the exact, at least apparently I didn't know the exact solution to this problem when we were working it on at hand. Maybe some of you in chat did. Obviously, the person who suggested it definitely did. Good job. And sometimes you'll do that. Like in the middle of solving a problem, you'll realize you found a bug and you have to work around it. And that's what we're doing right now, right? It does feel bad when your lecturer feels seems a little bit less prepared than he should be. But in an interview, this sort of situation does occur. And I don't dock the person if they find the bug in the middle. It's actually impressive if they can catch it in the middle here, right? So we would want to make sure that we don't remove the 5 in order to add the 6, in which case we still have 5, 4, 2, 1, 3. But at this point, we realized that here, we actually didn't need the k here. Like we didn't need the k plus 2. We could have stuck to k plus 1. All right. So the overall approach based on working out this example was, okay, we make a heap of size k plus 1, right, to count the k smallest elements inside. Let me just go ahead and explain mechanically why this works, right? If you look here, by the end of the iteration, this iteration, the heap should have the k smallest elements inside of it. All right. Which means that the next biggest element in my heap will be the kth smallest element. All right. Failure prompts growth. Yes, that's true. There's an idea in computer science education and education in general around fixed versus growth mindset. The more you believe that mistakes help you learn, and the more you ignore the idea that like, oh, you're either smart or you're not, the more likely you're going to be able to grow and go further. But if we look here, we can see that by the time we're done iterating through, right? Let's just imagine for a second we kept track of one less element. But here we didn't because I made a typo, I made a mistake, and then I made a second mistake, my bad. We know that the k smallest elements are in the heap somewhere, right? And the largest of those k smallest elements is going to be at the top, all right? Because every time we're removing an element that's larger than the element we're putting in. So the trick here, the dumb trick that apparently I forgot, was that only if the next element is smaller than the current largest in the heap. All right, so we're removing elements from my heap as long as we insert elements that are smaller, because ultimately by the end of this traversal, the heap should have the k smallest elements inside of it. It's weird that we're using a max heap to keep track of the k smallest elements, but that's kind of the trick. The nuance here was, as someone in chat said, make sure that you're only adding elements into my heap if it's smaller than the current largest thing, because that means that we'll always take out a thing that's too big to be in my k smallest elements and replace it with something that's smaller. All right. So approach number 3 is nuanced. There's a couple of different layers here to make sure we have the correct answer. We have this. We have the fact that here we can say that we have a max heap. It's going to be size k plus 1 at most. And then we're going to add all the elements in, and we only add it in when the array, when the heap is full, when the next thing we're trying to add in is smaller than the current biggest thing in my heap, which means that at the end of the day, after we go through all the elements, the heap should have the k smallest elements inside of it, which means that at the end of the day, if we call heap.extract max one more time, then we get the smallest element, so the largest element of the k smallest elements, which means that we get the k smallest element. Right now, runtime wise, people in chat are already starting to think about this. We know that every time we call a what am I trying to say? Every time we call heap add or heap extract max, it's going to take log of n, where n is the size of the heap. The heap now is going to be of size k plus 1, right? So every time we call heap add or heap extract max, it'll take log of k plus 1 steps, right? On order of O of that operation. We know for a fact that we will have O, in this case, of n plus k at worst case times log of k plus 1 steps overall, right? Before, when we were looking at approach 2 was to go ahead and add everything into a heap of size n and then call extract min k plus 1 times. This time around, we're going to go ahead and call add at most n times, and we're going to call remove at most, I think, n minus k times. Right? If we think about it, this is how many times we called add in the worst case. And in the worst case here, this is how many times we're going to call remove. Let me think about this carefully. K minus 1. Yeah, I believe this is accurate, because if we have a reverse sorted list, that's what we end up with, which if we simplify, we'll have k times log of k plus 1, which I would say is pretty good. Now, obviously, if k is close to n, then we're still doing something akin to O of n log n, right? So in the absolute worst case, if k is like n minus 1, let's say, we were trying to find the last element in the array, then we would end up with n log n. But now, if we had a k that's smaller than like here, then we would actually be really good, right? So if k is actually closer to, this is a tighter bound than what we had before, is what I'm trying to say. You would always have to look through the array completely, so it has to be n. Yeah, that's right. You are correct. It should be plus, I think n plus. Why am I getting this math weird? I'm having trouble with the math, I think, because of the mistakes I made earlier are throwing me off. But let me think about this carefully. If we go ahead and call, it would be additive. So we would have to add one more here, and then it would be this much. So yes. So it'd be 2n minus k, which we don't care about the 2 part. So we have n minus k here. If we, yeah. So it'd be roughly n here. Yeah. I think this is the best we're going to be able to explain it. So what people in chat are saying is that we go through and we're going to call add at least n times, right? We're going to add into this array a bunch. And so if we just trust that's true, and every time we're adding, we're going to take log of k plus 1. Even if we have to count some of the removes, this is going to be the overall runtime, right? Because we're going to have to call it n times, similar to how we had in approach 2, right? And if the k is close to n, then we're still going to do something akin to n log n. But most of the time, k is going to be somewhere in the middle, right? So don't mistake worst case as just picking the absolute most terrible thing. Think of it more as, okay, we know that this is going to be efficient in the vast majority of cases. All right. So this is an optimization for sure compared to approach number 2. Is k minus n minus k upper bound by n? Yes, it is, which is why we would have n here. That's another explanation for how n works, right? Because at worst, k could be equal to 0. Yeah, actually, that's a really good explanation. Good job pointing that out. So let's just think about this. K could be 0, in which case we would have 2n, which is still O of n times log of k plus 1. Or k could be something like n minus 1, in which case we would have this value be just 1, which is just, n times log of k plus 1 anyways, right? So this we know is going to be at most n and at least 0, which means that the overall runtime can be focused in on by this term instead. Yeah, in this case, if we're going to use comparison-based sorting, or if we're going to use a heap, n log n is going to be the absolute worst. If we pick a k that ruins us, then yes, we would have that as an issue, right? Okay. Everyone take a deep breath with me. Hopefully this was more understandable than me trying to make sure that I don't confuse myself. Let's go ahead and take a look at the next one. All right, this one was a little bit tricky. I linked the Geeks for Geeks explanation, which does a really good job of it as well. But now we're going to look at the third problem, which will be challenging in its own right. This is going to be on trees. It's so challenging. I gave you an example on its own. As always, what I'm looking for you to do for each of these problems isn't for you to be able to come up with a solution on your own. That takes lots of time and dedication and practice. What we need instead is for you to be able to answer the questions that we always answer. So in this case, what type of problem is this? What sort of edge cases could we have, right? And what have we learned in class that might help here? Right, I'll give you about 10 seconds for the first one. Is this a direct application directly from class? Is this a CS application, CS problem, or is this a real world problem? A, B, or C? Go ahead and type in if you have it. Yeah, people are typing in A, interesting enough, and a lot of people are typing in B. I would say that this is actually a CS problem. This is like not something that we've learned directly in class, all right? The way I know this is, let's take a look. We're gonna output, given a binary tree of integers, all the elements from left to right and top to bottom. So let's just look at the example and make sure we understand this. The first thing we're gonna print is the very leftmost element, right? The very leftmost element visually is 2, which is where this 2 comes from. From there, we're gonna print out 8 and 0, which means we're gonna print out these values. And notice we're printing out 8 and then 0 because we're going to look at this from left to right and top to bottom. In other words, we're going to print out all these elements because they're leftmost, but we're going to tie break by picking the 8 and then the 0 because the 8 is closer to the top. All right. If we follow that pattern, then we're going to get 5, 1, and 8 afterwards. And then lastly, 9, because that's the one on the very rightmost. Now, people are like, okay, this is probably A because we've done so many traversals. One of these must match, right? Well, let's go ahead and take a look at this together. If we were to do this breadth first search, I'll give you all 15 seconds. What would breadth first search output for this tree? If we were to do this in a breadth first search order, and we were to print out all the elements layer by layer, level by level, go ahead and type in chat. What do you think we should get? 5892108, right? We know that doesn't look like the output that we have originally, so that's kind of bad, right? Like, so BFS won't work. We have DFS. DFS has 3 versions. We have in order, we have pre-order, and we have post-order. If we did in order, what we would get is 2088159. Because we would go and we would print out the left subtree, print out myself, and then print out the right subtree. In other words, we're going to go left and then left again, print out the 2 because there's nothing on its left. And then since we print out the 2, then we print out the right subtree. So we get the 0 and the 8 afterwards. Then print out the middle here, right? Myself here. And then print out the 1 afterwards, which is where this 8 and 1 comes from. Print out the myself here, which is 5, and then print out the 9 afterwards, which is where the 5 and the 9 come from. So that, no good at either, right? So we haven't found anything so far in our set of things that we've learned that help. If we keep going, let's say we did pre-order, we know we're going to start at 5 because we print myself and then print our descendants, and that is a non-starter. We know that it starts at 5. Everything else doesn't matter because we started at 2 here, right? If we do post order, we know we're not going to print out this 2 first. We're going to print out actually 8021895, right? So none of these actually work. All right. Is it mirrored? No, even if you reversed it, you would still not get exactly, like even if you reversed one of these orderings, it would still not get this exact order. Or if you came up with something close, it wouldn't generalize. All right. So let's just go ahead and say this is a CS problem. It's not something we've seen in class. It's something that fundamentally you have to come up with a new solution for because we haven't seen any solutions for this in class. Right? Can we combine these? We will have to use one of these traversals because we're going to have to look at all of the elements in the tree at some point, right? But before we tackle this, one thing we could do in this case is that we need to come up with our own example. Let's just make sure we all understand what's going on here. So let's just imagine a different tree that looks like this. I'm going to make a tree down here, right? Every time we try to solve problems, we want to make sure we understand what we're actually trying to do. And so, for example, if I make another tree here, what should be the ordering of this tree? I'll give you all 15 seconds. All right, go ahead and type in chat if you have it. What do you think? We want to print out the 1 first in this case, and then the 6, and then the 5, and then the 8, and then the 0 afterwards. Yeah. Right, so if you have a question mark, if you're not sure, that's fine. Let's go ahead and look at this one step at a time. We want to print from left to right and top to bottom. In other words, we want to find the most leftmost element, which in this case is this 1, and print it out first. All right. 1 gets printed out first, and then we print out 6 because that's the next leftmost node when we're observing visually. Now, visually speaking, both 5 and 8 are on the same level of leftness. And as a result, we want to print the 5 first and then the 8, and then print out the 0 at the end. All right. Hopefully this clears things up, but this will make more sense as we keep going. But for now, let's just take a look at what sort of edge cases you think we might have, right? We've looked at 2 different examples now. We know we're dealing with a tree of integers. What sort of output do you think we might be a little bit confusing? Well, what sort of questions do you have about this problem, right? Again, we just want to make sure we understand this problem properly. So you're allowed to ask anything you'd like. I'll give you all about 20 seconds to come up with some questions, and then we'll tackle them together. And this is, again, what we would do in an actual interview. When you're prompted to solve a certain question, you don't just jump in and solve the question and start coding right away, right? No one does that, not even the best programmers. First, you have to make sure you understand the question. And so you have to ask yourself, hey, can I come up with my own examples like we did here in red? Hey, do I know all the edge cases and how to handle them like we're about to do? And like, hey, is there any other things I need to consider to make sure I really have a firm grasp on this before I dive in and start thinking about actually how to approach this? Okay, what questions do we have here? Go ahead and type in chat if you have them. Or question mark if you're not sure. Okay, let's see. Can we assume that the tree is null? No, you can't assume that the tree is null. So there's a lot of people asking, hey, what if we have an empty tree? Isn't taco night tonight? No, I ate tacos last night though. Other people are a little bit more confused. What if there are no left nodes? So if we had, for example, a tree that looks like this, only right nodes here, then what we would have is to print out this node first, followed by this node, followed by this node, followed by this node, right? If we have a null as input, then we just print out nothing, right? So one of the questions, for example, is null tree, right? What happens? How do we handle the null tree? Print nothing. Skewed tree, print starting at the left still, right? Now, some of you might have noticed that there's a weird edge case that we need to think about here. What I mean is, like, let's just imagine for a second that 1 had a left child. And let's say that left child is number 7 here. And that on its own, that this child itself had another left child, which let's say is 11 here. All right. So if we draw this out visually, we have a node that cross paths with another node. Because if you count the number of lefts and rights we had to take, they all end up in the same place visually for both 0 and 7, right? You go left, you go right, you go left. Well, you end up in the same place as if you went left and right. All right. If that's the case, what do you think we need to output for this situation? I'll give you all about 10 seconds. What do you think should be the output? Zero before the 7, left to right. Yeah, we would see 2, and then we would see 11 because we have an 11 here now. We would then see 8, 0, 7 in that order. 5, 1, 8, and then 9. Okay. And now some of you might not know why we picked this convention. Well, we just picked it arbitrarily so that we would have some good understanding of what we should do in this case. But this is what I mean by edge case. Like, it's not immediately clear whether or not we should print out, for example, the 7 before the 0, or if we just print out the 8 and then the 0 and then the 7 or something else altogether, right? Like, for example, if we had another node down here, let's say this was 1, do I print out the 1 before the 7, or do I print 0, 7, 1 instead? And that's the question that if you understood the problem fully, I would expect you to ask, right? And sometimes it comes up and sometimes it doesn't. But let's go ahead and think about how we would actually solve this. We just said that none of our normal approaches work here. DFS, BFS, they all didn't kind of work. And someone asked earlier, hey, when you were drawing arrows down, was this a hint? And the answer is yes, it was a hint. Let's just think about this really carefully. If we went ahead and labeled each node with some values, how would we approach this? Let's just say that we had 0, 0 here for 5. If we have 0, 0 for 5, let's just say we have 1, 1 for 9. If we have 1 for 9, what do you think we have for 8? What would labels or what values would we get for the 8? People are saying 0, 1. I'm going to say it's -1, 1. All right. I'll keep going and it'll be more clear in a second. This is going to be 0, 2. This is going to be -2, 2. This is going to be -1, 3. And this is going to be 0, 4. Let's imagine that each node has an XY coordinate where X is equal to how far away from the center you are, and Y is equal to how deep you've gone in the tree. If the 0 metric is just everything that aligns with the 5, the root here, then we know that there are 3 elements, this 8, this 1, and this 5, that have 0 as their X. Now, if we go to the left by 1, then let's make it so that the number goes down by 1. If we go left again, then let's make the number go down by 1 again. If we happen to travel to the right, then that X gets increased by 1, which is why that when we go to the right, this 0 is a -1 instead of a -2. Now, we also have another way of thinking about it. When we're going down, each time we're going down, we have +1, right? So we're actually making the problem smaller in that way. I'm not necessarily making it a matrix because all I have to do in order to figure this out is to modify DFS to label each node, right? So we could have DFS on the root and we would have 0, 0 being passed in recursively, which will call DFS on the root.left, which will make a recursive call here with -1 and 1, right? And then we'll also make a DFS on the roots left.left, in which case we'll have a -2, 2. And then if we do DFS on root.left.right, we would eventually make a call to -1 and 3 and so on, right? We can label each of these, and as soon as we visit a node, we can add it into a list. So at the end of the day, let's just imagine a list that looks like this. We'll have a list that looks like this. We'll have 5, 0, 0. We'll have 8, -1, 1. We'll have 2, -2, 2. We'll have -1, 0, -1, 3. 8, 0, 4. 0, 1, 0, 2. And then we have 9, 1, 1. All right. So all of this stuff is put into a list, right? The first value of the list is the actual value of the node. And then the second value is the X coordinate. And then the third value is the Y coordinate. So what we're actually going to do right now is to sort by the Y coordinates first. And we're going to make sure that this is a stable sort. If we sort by the y coordinates, then every single element that is close to the root goes on to the left, and everything that's farther away goes on to the right, which means that we're actually going to say, okay, we'll have this where it is. We'll probably keep this where it is, right? And then we're going to go ahead and move, let's say, everything that's this 9 here, this is going to move up by a little bit, right? And then we'll move everything that has 2 up as well. Let's just imagine we were sorting this by hand, which means that this is what we would do next, right? So this is what would happen if we stable sorted. Is there a way to undo? Okay, I can't bring that back. So let's say we stable sorted by the y coordinates first, right? And then stable sort by the x coordinates. In other words, we're going to go ahead and end up with a list that looks something like this. We're going to go ahead and move the smallest elements by left to right forward, which means that this thing with a -2 here, right? This is the x coordinate. It goes to the very beginning. Then we'll go and move everything with -1 to the beginning. And remember, we're doing this in a stable way. So since 8 showed up before 0, and they both have a -1 for their x coordinate, 8 should show up before 0 in the sorted version, because again, we're doing this stably. Then we do everything that had 0 as its x coordinate. Sorry, copy and pasting this and talking at the same time. Apparently that's hard for me right now. And then lastly, we have this 9, right? So that was step 3. At this point, step 4 is just print off the node values from this sorted list, right? And we get 2, 8, 0, 5, 1, 8, 9, right? Just the first value of these triplets here, which is literally exactly what we wanted originally. 2, 8, 0, 5, 1, 8, 9. Can we sort by x coordinate first and then y coordinate? No, you would actually end up with the wrong order. You actually have to sort by the less important coordinate first and then the most important, or you have to have one single sort where the tie break is handled correctly by looking at first the x coordinates and then the y coordinates, right? So if you remember the compare to method from homework 7, that's where you would put this logic where we compare the x coordinate first, and then if we have a tie on the x coordinate, we tie break by the y coordinate. All right. So see here, we had to do a couple of different things. We had to combine DFS with sorting in order to get ultimately the problem we want to solve at the end, like a solution for the problem at the end of the day, right? Oftentimes when we are trying to solve CS problems, they require you to combine multiple ideas all together at once. We know that DFS in this case, in step number 1, what's the runtime of DFS on any sort of tree? If there are nodes in the tree, how long will DFS take? Because we're going to look at every single element in the tree. What do you all think? It's going to be n, right? Because DFS, if you memorize it or if you just think carefully about it, DFS takes a look at every single element in the binary tree of integers. If it touches n elements, then there should be O of n overall. Right? So the first step takes O of n. And then the sorting is where things are tricky because there are n elements in this list every time. So this will be on order of n log n, because again, we're just assuming that we can't use radix sort here. We actually can't. Since you can't really sort this the way we would want because it's a bunch of numbers. It would be tricky to convert this into a dictionary sort or a bucket sort. Maybe it would be doable, but this would be n log n on both of these. And then printing this out would just be O of n because you just go through the list of n elements exactly once. All right. So then overall, the runtime for this approach that we've come up with overall is O of n times log of n. All right. Now, there is a lot of things that we had to do here. We had to first think about some of the more fundamental questions around like, okay, what are some edge cases? Do we understand the problem? Then we had to try, okay, let's try DFS. Let's try BFS. Do any of these work? And they don't, right? Then we had to think about, okay, what is the trick to doing this? And one hint that I might actually give if I were interviewing you is like, okay, what if we just had this idea of coordinates, right? Or like distance from the root, both vertically and horizontally. And hopefully you pick up on that and you realize you have to label each node and create this list here. And then you had to apply what you learned earlier, which is not only do you have to use a tree traversal, you have to sort the results of that tree traversal twice. First using the y coordinates and then using the x coordinates. Or if you know how to use the compare to method in Java, you could sort this exactly once using the y coordinates to tie break if the x coordinates are the same. And then at the end, we just print this out. Okay. I had one more question on top of this. We're done. We're not going to have time to answer it, so we'll just pause here. I want everyone to take a deep breath with me. Remember, what I want you to learn out of this slide and out of this lecture in general isn't the solutions or the way to solve all of these problems, but rather the approach that we took in answering questions that we had, trying to think about how this relates to the problems we've seen in class, and trying to come up with a solution based on the knowledge and experience and, trial and error, trying things out, right? Remember, even back here when we were trying to do case smallest, I made a bunch of mistakes here. And this is normal and common, even if you're working on the homework, right? It's not common for you to come up with the correct solution to your homework problem, let's say the first time around. And that's expected and that's fine. And on an interview, unless you compete and completely make all the mistakes, right, then you're not actually penalized for making small mistakes or not getting the answer right away. But what you need to focus in on is making sure that we are able to follow through all of the steps that we did here, and that you see how we were able to come up with a working solution by the end of the day. How much time would we usually have for something like this in an interview? If you were to write this version of the code, I would want you to write it within the first 20 minutes of the interview. And then you would have about 25 minutes to write a version of this that runs in O of n. This runs in n log n, which is not the answer I would be looking for. You would actually have to keep working and improve this and make this faster, which is scary, I think, for some of you. You're like, I don't even know if I could write this in 20 minutes. How the heck do you want me to improve it in 25 minutes? Remember, this is after literally months of study, if not longer. People get good at this because they take like months of studying, like week over week. Even if you do really well in this class, you'll still have to practice a lot in order to do well overall. You'll have to do a bunch of mock interviews. You'll have to solve a bunch of these problems here on your own. So I don't expect you to all be able to magically come up with like an O of n solution in order to like solve this, right? What if it was a real world problem? I mean, usually interviews take anywhere between 45 minutes and an hour, and you might solve anywhere between 1 to 3 problems during that time. For those of you who are interested in coming up with the O of n solution, you want to create a map of integers where the let me just write this out first. You want this data structure. All right, you want a map whose keys are going to be the column indices, so the y values here. No, the x values here. And then whose values are going to be the list of node values that reside there. So for example, in this case, you would want a dictionary who, for example, -1 maps to just the list with 2 in it. -2 maps with the list with 2 in it. -1 maps to the list with -1, 8 and 0. 0 maps to the list of 5, 1, 8. 1 maps to the list with just 9 in it, right? These values come from just picking the values of the nodes and going through down column by column. You would actually have to use a breadth first search here. And then you would have to update this map as time goes on. And you would have to modify the breadth first search in order to actually keep track of the column indices, as well as find a clever way to print this map at the end of the day, since it's not ordered. All right. If you didn't understand at all what I was talking about on the top right, that's okay. You can ignore it. That's way outside of the scope of this course. So you don't have to care about the blue stuff on the top right here. All the other blue stuff you have to care about. All right, so let's go ahead and stop here because I believe we're at time. Let's do takeaways. Oftentimes you get stuck writing algorithms because you have a hard time coming up with the idea. Unfortunately, I don't have a good way to help you with that apart from basically showing you a bunch of different kinds of problems, making sure that you're asking the right questions every single time, and then practicing a bunch. There's a quiz on this sort of stuff on dynamic programming and coming up with the idea on Thursday for you all. But remember, I'm not going to expect you to be able to magically solve problems. What I'm really expecting you to do is to answer the set of questions for certain problems that we have here, the questions to ask here. That's really what we'll be focusing in on, right? And then there will be maybe some of the problems will require a little bit of what's the approach, right? But they should be a little bit easier than the problems we saw today. Okay, so remember, I'm showing you stuff that is inherently hard. It will take months of practice for you to get to this level, right? Certain companies will expect you to code on this level in the time that we have, but not all of them. And to be fair and clear, a lot of companies will ask you this type A type question more than anything else, right? And a lot of the companies will ask questions that are maybe on the easier side compared to the questions that we asked today. Okay, so don't freak out. Don't get discouraged. I promise you, you will get a job after you graduate. I'm not showing you stuff that you absolutely need to know. I'm showing you problems that are generally very challenging. And I wanted to show you how you would apply yourself even on some of the more challenging questions, because some of you, may apply for some of these companies. And I want you to make sure you understand what the expectations are, right? Okay. That's all we had for today. If you have any other questions or concerns, feel free to ask. Remember, right now we're in office hours, so you can ask me any questions you'd like. Thank you so much for your time, and I'll catch you later this week. Take care.